Assalamualaikum and good morning. Now, Group 10 want to present about our um, programming project, Steam Power Plant. Our members is Muhammad Syaiful Malik, Muhammad Dini Syafizi, Muhammad Syafiq Afzan, and my name is Amirul Harid Iskandar. Our definition about our project steam power plant is a steam power plant is a thermal power system that convert heat energy into mechanical and then electrical energy using the Rankine cycle. Our purpose for our project is to understand how steam-based energy system operate and apply thermodynamic principle, first and second law in real-world energy conservation. There are 5 processes that involved in this steam power plant. First, boiler heat addition. 3. Turbine mechanical work, and other one is condenser heat rejection and pump fluid circulation. And our objective for this project is to stimulate and analyze the steam power plant in MATLAB, observe system performance, and explore the effect of operating condition on efficiency. Now is about coding implementation part. First, the input section. User input boiler and condenser pressure or VIA GUI. Optional. Turbine and pump efficiency if included. Validate that boiler pressure, condenser pressure interface built using UD file or UBython. And second is calculation section. Call through run Rankine function. Use xsteam.m to obtain enthalpy H, entropy S, specific volume V, that compute pump work, turbine work, network output, heat output, thermal efficiency based on thermodynamic. And lastly is about output section. The display is all calculated value of work, heat, efficiency in GUI. Plot T diagram to visualize thermodynamic cycle. Show warning message for invalid input. Provide clean user-friendly interface.
Next is system description. The system model is a steam power plant operating on the ideal Rankine cycle commonly used in the thermal power plants. The cycle converts thermal energy into mechanical work and then into electrical energy through four main components, which is first component is the pump compress saturated liquid water isentropically to boiler pressure. Second, the boiler heats the pressurized water at constant pressure until it becomes superheated steam. Third, the turbine expands the steam isentropically to produce mechanical work. And finally, the condenser condenses the steam back into liquid at constant pressure and temperature. This fourth process operates in a closed loop to continuously convert thermal energy into mechanical and ultimately electrical energy. This is TS diagram or temperature versus entropy diagram. It provides a thermodynamic view of the cycle. This diagram shows two vertical lines that represent the isentropic process, which is in the pump and turbine, and two horizontal or curved lines representing isobaric heat transfer, which is in the boiler and condenser. Each segment of the cycle has a specific energy function. First, heat is added in the boiler from point 2 to 3. Mechanical work is extracted in the turbine from point 3 to 4, and heat is rejected in the condenser from point 4 to 1, and work is input in the pump from point 2 to and work is input in the pump from point 1 to 2. This diagram connects the system physical component with how energy behaves and transforms throughout the cycle. Next is methodology. There are three parts in the methodology, which are modeling approach, list of equations, and assumptions made during modeling. So to analyze this cycle computationally, the model was developed using MATLAB with the XSTEAM function, which supply accurate thermodynamic process for water and steam. This is how the simulation works. Mm, The user provides boiler and condenser pressure through a GUI, and then XSTEAM retrieves entropy, temperature, and specific volume at each key state. Using this data, thermodynamic equations are applied to determine heat input, work output, and efficiency. The result is including turbine and pump work, heat transfer, and cycle efficiency are then displayed along with a TS diagram for visual interpretation. This approach this approach allows us to evaluate how pressure change affects cycle performance under ideal condition. For for the list of equation, pump we can see the pump work. Pump work is calculated using specific volume and pressure difference. Boiler heat input is based on the enthalpy increase from pump outlet to turbine inlet. Turbine work is the enthalpy drop from turbine inlet to outlet. Mm, Heat rejected in condenser mm, use the enthalpy difference from condenser inlet to pump inlet. Net work is the difference between turbine and pump work. And finally, thermal efficiency is calculated to evaluate the overall performance of the cycle. Alongside the uh, equation, we can see the assumption during modeling, which is we assume to simplify the modeling process. The following ideal ranking cycle assumptions are applied, which is the system operates under steady state condition. The fluid is pure water or steam throughout the cycle. And then the pump and turbine are isentropy. And last, the boiler and condenser operate at constant pressure. This simply this simplification allows us to isolate and study the effect of different pressure on the Rankine cycle's behavior without introducing unnecessary complexity.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Syaful Malik bin Zuharim. My metric number is 102713. Today I would like to talk about the graphical visualization. So this figure it shows the temperature versus the entropy diagram. And it also illustrates the ideal Rankine cycle, which also did serve as a fundamental thermodynamic model for the operations of the steam power plant. It also indicates the phase transition and the energy changes by the working fluid, typically water or steam, but in this case it's steam. It progress through the four principal components, which is the pump, the boiler, the turbine, and the condenser. So at this point, 1 to 2, the boosting water has been done by the pump. It has work to do. Then after just a little bit, pump a little bit, then we heat it using the boiler. Heat it until the temperature is constant. Then when it's the constant, it will become a saturated water. Then we heat it up until it reaches the superheated vapor. Then the next thing is the turbine will be will doing it works. Then at this point, the heat dissipation will be occurred by the condenser until this point again. So this area surrounded by this line is represent the workload by the cycle. Each one of these it has work to do. So This blue line is indicate the saturated water line. This yellow line is saturated vapor line. This is the general graph of the temperature versus entropy diagrams. The next one is the visual the diagram the visual by the MATLAB. So these graphical visualizations, it shows the temperature and the entropy diagram. It also illustrates the ideal Rankine cycle, but using a UI figure, which also serves as a fundamental thermodynamic model for the operation of a steam power plant. So in this diagram, we use the boiler pressure, which is at megapascal, and the condenser pressure, mega 0.008 megapascal. In this diagram, we have found several variables. This one, such as condenser, pump work, turbine work, network, heat supply, and cycle efficiency. And we move to the user interface. We use the simulation tool that features a graphical user interface using MATLAB. This interface will interact with the user with the Rankine cycle model and consists of the following components. The first one is boiler pressure input. It is a numeric input that accepts the boiler pressure in 0.1 megapascal to 330 megapascal. It also valid due to thermodynamics condition under certain conditions. The second one is condenser pressure input. It is also another numeric input for the condenser pressure, but it also limited between 0.001 megapascal and 0.2 megapascal. It also reflects the typical operation limits for the condenser in steam power. And the third one, the simulation button. It is a push button that run the simulations. It will trigger function to process the input values and perform thermodynamic analysis using the xdim function. The fourth one is result display. It enables users to view and interpret results easily. And the last one is the diagram plot area. This is a plotting axis that displays the temperature versus entropy diagram. This visualization represents the fluid that thermodynamic states and transition through the cycle for processes. This one. Okay. Next one is the instructions. The instructions is start the program. Then the parameters will be the parameter for the input will be displayed. To ensure cycle viability, the boiler pressure must always be higher than the condenser pressure due to the certain condition. And the third one is launch the simulation. So the system will be convert input units to specifications. The second one is for every cycle state, carry out the required computations. And the third one, calculate the thermal efficiency and energy balance. The fourth one is create a TS diagram. And the fourth one is examine the finding key performance indicators will be shown in the result panels. We can examine how the fluid changes behavior over the course of a cycle and how various input affects system performance. And the last one is to adjust and rerun. It, it, ha- it is to investigate the effects of various operating conditions on cycle efficiency and work output. We can change the simulation input parameter and run it again to avoid the parallax error. Thank you.
Next, I will be presenting the result part. So this part shows an example of a successful simulation using our MATLAB default user interface to represent the Rankine cycle. So we use this value. For boiler pressure, we put 8 megapascal. For condenser pressure, we put 0.008 megapascal. Based on these inputs, the simulation produced the following results. So for the turbine work output, is approximately 1266.16 kJ per kilogram. For the pump work output is about 8.06 kJ per kilogram. for the net work output of the cycle is 1258.10 kJ per kilogram. The heat supplied to the boiler is 3167.62 kJ per Pascal, and this results in a thermal efficiency of 39.72%, which is a reasonable value for an ideal Rankine cycle under subsequent conditions. In addition to the numerical result, the graphical user interface also generated a temperature versus entropy result, a graph which we can see in the right, which visually represents the Rankine cycle. So this diagram helps user to understand how the working fluid moves through each stage of the steam power plant, showing the heating, expansion, condensation, and compression process clearly. Next, we move on to the discussion part. The result from our MATLAB simulation successfully validated the theoretical principle of Rankine cycle. So we observed that changing the boiler and condenser pressure had a significant effect on both efficiency and work output. For example, using a high boiler pressure of 8 MPa improved the thermal efficiency by allowing the steam to expand more effectively in the turbine. On the other hand, using a low condenser pressure of 0.008 MPa increased the work output by maximizing the enthalpy drop during expansion. As a result, the simulation achieved a thermal efficiency of 39.72%, which is reasonable for the basic Rankine cycle under subsequent conditions. While the actual system may include energy losses that reduce performance, this simulation still provides a realistic and reliable estimation. And next, we move on to the real-life application. So these findings are highly relevant to real-world power plant operation. In actual steam power plants, engineers raise boiler pressure and temperature to improve efficiency, just like we did in the simulation. They also implement the advanced features such as heating and regeneration to boost cycle performance even further. Our simulation helps highlight this practical design consideration and shows how adjusting operating conditions can lead to more efficient and sustainable thermal power generation. Next, we move on to the conclusion part. To conclude our project, we successfully simulated a steam power plant using MATLAB based on the Rankine cycle. The user inputs such as boiler and condenser pressure allowed us to calculate key thermodynamic values. Through the GUI, we display important outputs like pump work, turbine work, net work, and thermal efficiency. We also use a temperature versus entropy graph to visualize the energy flow in the cycle. With a boiler pressure of 8 MPa and a condenser pressure of 0.008 MPa, the simulation achieved a thermal efficiency of 39.72%. And next, for the effectiveness of model and code, the model worked effectively and followed thermodynamic theory with no major errors. We used the xSteam function to get accurate steam properties for each state in the cycle. The GUI helped users interact with the system and understand the result more easily. And overall, the simulation clearly showed how changing input values affects the performance of the system power plant. Next, for the improvement and future work. So for future improvement, we suggest adding advanced features such as reheat and regeneration to improve the cycle efficiency, including real-world losses like friction and non-isentropic processes would make the model more realistic. The user interface could also be improved by adding more graph and visual elements to support this learning. Lastly, this model could be expanded to stimulate more complex thermal systems for deeper analysis. Next, this is the references part. So these are the references that we use in completing our group project. So that's all from group 10. Thank you.